Propositional logic operations were created to test the truth or reality of different conditions or statements. Statements such as, "the shape is a square," are called predicates. Then, for each predicate, we could use an analogous Boolean variable to represent the truth of the predicate. This variable would be 1 when the predicate is true, and 0 when the predicate is false. For a different predicate, we would use a different Boolean variable. We can combine predicates and create new statements. For example, this statement will be true only when both smaller predicates are true. In this situation, we represent the new composite statement with another Boolean variable. Now, let's discuss how we use Boolean variables to describe the behavior of the logic gates. The NOT gate receives one input and transmits one output. And this is exactly what you might think. It turns values into their opposites. This is the symbol for the NOT gate, or inverter. When you input a 1 into a NOT gate, it outputs a 0, 1's opposite. Similarly, when you input a 0 into a NOT gate, it outputs a 1. We can represent the NOT behavior with something called a truth table. A truth table typically has two sets of columns, the inputs and the outputs. As you can see, the output of a NOT operation is the opposite digital value. When we write Boolean expressions, we represent the NOT function with the following notations. I will use the top notation most often during this microlecture series. The AND gate receives two inputs and transmits one output. The AND gate outputs a 1 when both inputs are 1, and outputs a 0 for all other input combinations. The AND function can be represented by the following notations. Again, I will predominantly use the top notation during this microlecture series. The OR gate also receives two inputs and transmits one output. The OR gate outputs a 1 when either or both inputs are 1, and outputs a 0 when none of the inputs are 1. This OR is called an inclusive OR. Again, I will predominantly use the top notation during this microlecture series. The word OR in English is ambiguous. It can refer to either the inclusive OR or the exclusive OR, called XOR. To demonstrate this ambiguity, we will compare the inclusive OR with XOR. The XOR gate receives two inputs and transmits one output, but the XOR gate outputs a 1 when exactly one of the inputs is 1. The XOR is exclusive because it excludes the case when both inputs are 1. So, when you ask a friend if they want vanilla or chocolate ice cream, this question can imply an inclusive OR because your friend could very well ask for both types of ice cream, and you may grant that request. If you must decide whether you turn left or right, then this decision implies an exclusive OR, because you cannot turn in both directions. To conclude, here is a slide that presents all four of the operations that we just discussed.